Hi, and welcome to Math 1B03. In today's lecture, we'll be doing lecture 29, and we'll be talking about section 5.2 of the characteristic equation. As you can tell from the background, I'm still in my office. I'm actually doing lecture 28 and 29 back to back today. So just to kind of recap of where uh, we were looking at what an eigenvector was and an eigenvalue, and a vector x is an eigenvector if it's a non-zero vector, and it's an eigenvector of a matrix A if A times x is equal to some scalar multiple times x. So basically multiplying the vector x by the matrix A gives you back the same vector up to some scalar multiple. So you've only kind of stretched or shrank the vector, or you may have pointed it in the reverse direction. Now, today what we want to do is actually spend a lot more time getting you comfortable with computing both the eigenvalues and the eigenvectors of a matrix. In order to find the eigenvalues, we have to define what a characteristic equation is. So the first part of today's lecture will be looking at the characteristic equation, using that to find eigenvalues, and then we'll do some examples of finding the eigenvectors as well. Okay, let's make myself disappear here. I'm just going to make sure that I have disappeared. Yes, I have. Okay, and let's start on with today's lecture here. So first of all, we're going to do look about the eigenvalues, how to find the eigenvalues. And the eigenvalues are encoded in this object, which is called the characteristic. Can't spell characteristic. Let me try that again. So encoded inside of what's called the characteristic polynomial or equation. So we'll talk about what that means in a minute. But we're going to start with an example. So hopefully from the example, you can understand what's going to happen in general. So let's say we wanted to find the eigenvalues of this 2 by 2 matrix 2, 7, 7, 2. So we want to find an eigenvalue. And from last class, we know that that means that we can find a non-trivial solution. Okay, so to this equation. So we have a non-trivial solution to this equation. But you can rewrite this so that we have matrices on both sides, right? We have AX is equal to lambda I2 times X as a non-trivial solution. And because they're matrices on both sides, we can rearrange the equation and then factor out the X. And we get A minus lambda I2 times X is equal to 0. And this has a non-trivial solution. So we want to decide whether lambda is an eigenvalue, and we have to check whether this system or not has a non-trivial solution. So there's a bunch of different ways that you can do it. You can, try to row reduce your matrix and count the number of free variables. But what we really are just interested in is more of an existence question, is yes or no, is there a non-trivial solution? And one way to get at that information was actually without finding, which variables are free and so on, is to use the determinant, right? So this will happen if and only if the determinant of this matrix is equal to 0. Okay, so let's put this observation into practice. See, where was I going to do it? Okay, I'm going to do it over here. So we want to look at the matrix A minus lambda I2. We don't know what lambda is, right? That's what we're trying to find. So, but we know what A is. It's 2, 7, 7, 2. And lambda times I2 is the matrix with lambdas all down the diagonal. And so we can simplify this and we get 2 minus lambda, 7, 7, 2 minus lambda. So that's our matrix. And we can now compute the determinant of this matrix where we're treating the lambdas as unknown. So the determinant, right, is you multiply down the diagonal and subtract down the diagonal, anti-diagonal. So we have 2 minus lambda times 2 minus lambda minus 7 times 7. So we can simplify this as 4 minus 4 lambda plus lambda squared minus 49. So this is equal to lambda squared minus 4 lambda minus 45. So that's the determinant. And what we want to know is, when does this thing equal 0? Well, this is equal to 0 if and only if lambda squared minus 4 lambda minus 445 is 0. But you can factor this as lambda minus 9 times lambda plus 5 equals to 0. And so this will equal to 0 if and only if lambda is equal to 9 or lambda is equal to negative 5. So what we have here is the answer to our question, which is that the eigenvalues are lambda equals 9 and negative 5. And if you remember what we learned from the previous lecture is that an n by n matrix will have at most n eigenvalues. And so since we have two eigenvalues, a 2 by 2 matrix, we can expect at most 2 eigenvalues. So there's no more, we can't expect any more eigenvalues than this. Okay, so this approach generalizes, right? This argument here that we did right here, there's nothing special about a 2 by 2 matrix. I would just put an n right here. So lambda is going to be an eigenvalue if and only if this equation is equal to 0. And so that's what I have here, that this approach generalizes. Let's say I have an n by n matrix. The equation, determinant of a minus lambda I n equals 0, is what's called the characteristic equation. And if we don't care about setting it equal to 0, we're just interested in the equation on the left-hand side, we call that the characteristic polynomial. So we're going to pause here, and then I'm going to give some more examples of finding the eigenvalue, looking for the characteristic equation and the characteristic polynomial. And I haven't actually made this a little bit explicit, and I'll make it explicit where are the eigenvalues. Okay, we'll take a quick break, and I'll see you at the next part.